Okay, great. I just had a quick little snack. Maybe we'll wait like 2 or 3 minutes, make sure people are coming back.
Maybe we could use the few minutes just so that everybody can try whether MCell works correctly on their side. Just to load an example and run it and plot.
Okay. Sure. So I'll share my screen.
So that we can resolve any potential issues earlier.
Sure. So this will kind of double as the tour of the examples and the Cell Blender workflow. Okay. So if you've got Blender open and you have your splash screen, I mean your world, let's start by selecting everything in the world with the A key on the keyboard, and then hitting the X key on the keyboard to delete everything. And a little pop-up pops up and you have to click on the word delete in order for it to do it. If you move your mouse outside of that, it goes away. So you have to hit X and then click on delete to confirm it, and then boom, everything's gone.
Okay, maybe Tom, okay, so sorry, maybe if you wanted to like do this right now to show the examples, maybe you can like wait.
Yeah, we're gonna,
okay. So
okay.
I'm not completely sure what's the plan.
Okay, because it's kind of hard to get people to test it without showing them how to test it, right? So
yeah.
I need a little bit more of a little bit more explanation. Okay. Someone wrote in the chat. Yeah, so Randy asked about setting units in Cell Blender. Yeah, I'll show you that. Maybe I can show you that right now. Michael says attempted to add torus mesh, but the dimensions were locked out and unable to be edited. Okay, well, we might get to some of that. Okay, so maybe everyone's back now. So what I did, well, I have global undo, so I can undo what I did. Hit, see, command. Where's my undo? There it is. Okay, so I hit guess what, Option Z or Command Z. I think it was Command Z on the keyboard to bring everything back because I had deleted it. So A key on the keyboard to select everything. X key to delete, and confirm delete by left clicking on the word delete. It's gone. If I did, and then, and then Command Z to bring it back. Okay, but delete it. Okay. And now to get to the tabs that let us control kind of the numeric the numeric properties of our scene. The N there's a collapsed toolbar over here that you can get to by clicking on that little caret right there, or you can also hit the and you can see I can get to that, and to make it go away. Oh, that's not how you make it go away. There's not a good way to make it go away. Or I can drag. I can find along the edge of it, and I can drag it all the way back, and it's gone again. Or the way I like to do it is hit the N key on the keyboard, which stands for numerics panel, and brings up the numerics panel, and again hides it. N to show it, and to hide it. When it's showing now along the right-hand side, we can see the different toolbars, tabs for the different toolbars. and we won't go over these first two. We can see Cell Blender, Gamer, and NeuroPil tools. These three things are components of the Cell Blender tool suite. And Cell Blender, you click on by just click on it with the left mouse button, and you can say initialize Cell Blender. And then you get the Cell Blender tab, and it comes up pretty small. So I like to go along the left side of it and click and drag maybe about like that much. So you can see all the words. And now, so if you've gotten this far, then probably Cell Blender is working fine, but we haven't shown that MCell is working fine. So to test, to make sure your MCell installation is working fine, we're going to go to examples. and these are the tabs. Anyway, for the workflow in Cell Blender is has a bunch of these tabs that let you, control or configure, define, create different parts of your model. But there's also an examples tab that has some built-in predefined examples. And you can click on any of these tabs and bring up the control panels for them. But let's go to the examples tab. And probably a good one to start with to try is maybe the Fix Law 3D is a good one to start with, a good example one to start with. So I'm going to click on Fix Law 3D. And when I do that, it's going to basically read a configuration file, a model definition file, and create that whole model. And there it is. And like earlier, I can middle click and drag and rotate this around. This model consists of a bunch of concentric spheres. But let's not worry too much about the details for this model right now. Let's do a test run to make sure our MCell simulation, MCell setup is working correctly. So you'll notice, well, if I go, so to do this, go to the Run Simulation tab. So the Run Simulation tab doesn't run the simulation when I click on it. It pulls up the option to run it, or the controls for running it. And you can see there's a message in here that says open or save a .blend file to set the project directory. So the workflow in Cell Blender is that you are editing, creating a blend file in Blender that is the configuration for your model. And but when you run the model, we have to have a place for where the results of the model are stored, and all the properties and everything for making the model run, those have to be stored somewhere. And in order to do that, we first have to have a blend file, and this is a brand new one. It hasn't been saved. Doesn't know where it lives on the file system because it doesn't live anywhere in the file system. I have to save it, right? So, so the first thing you do is you go to File, Save, or Save As. But since it's the first time I'm saving it, those are going to be the same thing. I'm going to go to File, Save, and I'm going to navigate to a directory where I want to store it. And I've already made a directory on my system called, users Bartol CMW 2021. But maybe when you first open yours, that's because I've been using this, and maybe when you first open yours, it just says your home directory under Bartol, or whatever your name is on your system. And navigate to where you want to store it. So I can see I've got this folder I made called CMW 2021. And so I click there, and then that's the directory I want to put it. If you want to create a new directory, you can navigate to a directory, and then if you want to make a new directory, you can click next to the directory name up here in the directory thing and just type in the name of a new directory. like, I'll just call this first test or something. And when I type in that name, it's going to say, I'll create new directory, right? If that exists, it'll go there. But if it doesn't exist, it's going to give me the option to create it. So I'll just say, create new directory. And so here I am in this new directory. And then down here at the bottom of the file navigator is where I type in the name of the file. And I might call this, after the name of the model, Fixed Law 3D, or you can name it whatever you want. I'm just going to say Fixed Law 3D, and then you just say Save Blender File over in the lower right-hand corner to save it. Now the model is saved. And after I've saved the model, now the Run Simulation tab gives me all the options for running the simulation. Okay. And the main button you're going to want to click on, so I can control the number of iterations that I want to run and the time step. And you can see here, this says iters and DT. These are the names of parameters that are in the parameter section. So this model we just loaded as an example, but this is a fully configured example, and it has a bunch of parameters in it. We'll learn more about this as we keep moving with the tutorial. But let's go back to the run. I just wanted to show you that this is where these values are coming from, iters and DT. And then we click on export and run. So when I click on that, what's happening is Blender and the Cell Blender add-on are converting the model into a form runnable by MCell 4. What it just did was it created a directory in the same directory as where the file was stored. It's making a subdirectory there where it exported all the files necessary for MCell to be able to run the model, and then MCell ran. And when it ran, it gave us what seed was being run and what percentage of the simulation was finished. It gave a countdown. It also gave us the process ID in case something goes wrong. We could use that number to kill the job. We can also kill it by clicking on these kill buttons underneath. But the simulation just ran. And this means it succeeded, but let's look at what its viz output was and visualize it. I can click on reload viz data, and it just loaded in the visualization of the particles in the middle there. And then at the bottom of the 3D view window, this space here is called the 3D view window, are some VCR controls, basically, or play controls, where I can play forward or backward. I'm going to hit play forward, and you can see the particles diffusing through the space. And so that is kind of the workflow of how to load in an example and save it and run it and visualize it, just as quick and snappy as that. And hopefully that worked for everybody. And if that worked for everybody, so some people are saying may have missed a step. Susanna says may have missed a step.
Hi. Yeah, so I hit run simulation and it took a while to run, and now it seems like it worked, but nothing is being released.
So what you have to do is click on reload this data.
Oh my God, not this.
Yeah.
Yeah, that's what it is.
Okay.
Okay, thank you.
Yeah.
Tom, sorry, this is a problem. When I hit reload visualization data on the Mac, it does not do anything, even though it sits on as 100% complete. So everything as you see on your screen, exactly the same. So load the model. Well, the problem is, it's just when you click reload visualize data, it doesn't do anything. I don't know why.
Well, you might see a subtle change, and then you have to go down here and hit play. To
Oh, hit
play it.
play. Oh, okay.
Yeah. I was moving.
Oh, okay.
Yeah,
Thank you.
Yeah, I
it
was
worked.
moving a little. Yeah, moved a little faster. Yeah, it would have been a very subtle change, right? So here it is at the, yeah, so in these VCR controls, I can also play backward, forward, but, and then if it's playing, I can hit pause to stop it. I can, and then this is, jump to the beginning. I can also jump to the end. Like this, I can move in and out. I can middle click and drag and, look at this from different angles. Okay. We'll be doing more detailed hands-on here, but Adam was nervous that, and so am I, that that people were going to have trouble getting this to work at all, and so this was kind of a proof that everyone's, hopefully everyone's Cell Blender and MCell installations are working correctly, and you're all able to see. So if anyone had trouble or is still having trouble seeing this, please say it doesn't work in the chat or something, and we'll get you going. So Susanna says the resolution of my particles is really low. So if I now I'm zooming in and out. So yeah, Susanna says she's going to post a screenshot on Slack. I'm not sure what will be going on. Susanna, what OS are you using?
Windows.
Windows, okay. Is it Windows 10?
Yes.
Yeah, okay. Yeah, I'm not sure why it would be. How about how do your control panels look? Do they look?
Yeah,
with
everything
nice?
looks. Yeah, everything looks normal. And I've just posted it on Slack. They look, when I try to zoom in, they look super pixelated and like yeah.
Yeah, if you
it
zoom
just
in, they
looks
should
odd.
look really nice like this.
Nope, that's not how they look for me.
Huh, okay.
I would guess that maybe Blender fallbacks to some maybe CPU rendering.
Yeah. So yeah, so maybe Susanna, you don't have a good graphics card in your machine?
Maybe, but it worked. It's never given me this problem with Blender before.
Huh.
Yeah, maybe the previous version didn't have such requirements. I don't know how to say.
Okay.
Yeah, the new Blender is fancier.
Anyway, from the image where you posted, it looks like that the shading is really like heavily simplified.
Yeah. Is there something I can do on the preferences to set preferences to solve this?
Well, I haven't encountered that before, so I'm not sure what the setting would be, but maybe we can work on it during the lunch break or something.
No problem. Yeah, thank you.
Okay, sure. Okay.
I'm sorry, quick question. Why would be individual molecules as the cubes? Is there a reason for that, or?
Why are what?
The individual molecules, right? All of these dots, the green solid dots are individual molecules.
Yes.
Why are they cubes? Not, I mean, I don't know, maybe it's just.
Yeah, so there's a way to control all of that, and you'll be seeing it when we do the real workshop. I mean, when we real workshop, I mean, when we get to the real stuff, coming right now.
Oh,
Okay.
right.
Yeah. So, okay. So now we know everyone's system is working. So let me just show you. I probably won't run these because I don't want to take too much time, but just show you that in the examples, we have a whole lot of things happening here. We have 1D and 3D diffusion examples, examples of change of variable rate constants in a model, models of direct transport, where the molecules, well, if I load the direct transport example, I can look at the reactions. And in direct transport, we have molecules, a volume molecule binding with a surface molecule, and then immediately being transported across the membrane from inside to outside in one step, basically on collision, right? This is transport through the membrane on collision without an intermediate. So that's what we call direct transport. But this is kind of jumping ahead to some syntax that you haven't seen yet, but you're going to. A delayed transport reaction has an intermediate. So V at in plus S makes SV, which is the bound intermediate. And then SV can transport across the membrane in a separate step. You can see both of these are irreversible reactions. So the syntax of reaction is pretty much identical to BNGL language. It can be simple without these annotations, and simple without any components, or it can be with components and bonds and everything that you saw yesterday. The in and out here are keywords in the MCell language and the MCell variant of BNGL that eventually will make it into the compartmental BNGL language. We'll talk more about that later. And then direct transport with compartments is another example where we actually now have two compartments. This is a compartmental BNGL model, basically. And its reactions look like this. And now this looks a lot like what you were seeing yesterday with compartmental BNGL, where I have, instead of in and out, which are special keywords we'll get to momentarily, we're using the ordinary, currently supported CBNGL, compartmental bionetgen language way of expressing compartments, where we say V at cube plus S at membrane goes to S at membrane plus V at world, where we have compartments called world. Up here is the compartment. When you click on objects, you can see up here in the upper left-hand corner, whatever object you clicked on, its name appears up here. So we have a thing called world and another thing called cube. And so we can have reactions that transport across membrane. And again, this is the direct transport version where there's no intermediate. We're just going directly across the membrane from V at cube goes from outside, this is inside, cube is this volume. So V at cube means anything inside here. Can hit S on the membrane. And then the S on the membrane stays, isn't changed. And the V is transported across the membrane from being inside the cube to being in the world, which is outside of the cube, right? And another example, we have Laco-Volterra reaction. I think Lupe is going to be telling us about that on Friday. Is that still the plan, Lupe? I don't know if Lupe is here right now, but I think she'll say yes. And then this is the model we're going to build today. So I'm not going to show you that because that would be a giveaway. We have something that we talked about earlier today was how does a E. coli decide when to divide and how to divide itself in half. That is accomplished by a biochemical reaction pathway in E. coli called the Min-D, Min-E system. We have a model of the Min-D, Min-E system implemented in spatial agent-based particles with MCell right here. We have a lipid raft model, which has particles diffusing on the membrane that can go into different rafts. We have the LR-BNGL model, which Jim talked about yesterday, one of the examples that he talked about yesterday. Its reactions are, except this one's more complicated. This one can make polymers because the L molecule has 3 places to bind R. Has 3 places to bind R, and the R molecule has 2 places to bind L. Well, you'll be seeing more about this as we work more with these models. I'm just kind of giving you just kind of an overview of the examples that we have here. we have the FC epsilon R1 model that Jim talked about yesterday, with spatial compartments, and with all of the reactions between Lin and Rec and Sick, all here. With all, and this is the complete version of that model, or some variant of the model, maybe not exactly the same one that Jim showed yesterday, but some variant of that model. And we have one of my favorite models, the rat neuromuscular junction model. This was the system that I studied as a graduate student at Cornell, the neuromuscular junction with 2 electrode voltage clamp. And it was the system in which we, when studying it, first devised spatial Monte Carlo method with MCell Pt.1 and MCell Pt.1, and was the origin story for where MCell came about. And so that model's in here, and you can see it has a very complicated membrane. And then there's a number of other models in here. So there's one here called periodic boundary conditions, but periodic boundary conditions only work with MCell version 3. And this cell blender here and the MCell that you have installed can run in MCell version 3 mode. So it still has the ability to run any old MCell models that you have from before. And there's a number of models in here that are MCell version 3 models. And these in particular demonstrate, this one in particular, see what just happened. Something bad just happened, I think. No. Somehow it didn't. Uh-oh. Oh, there it goes. All right. It was just had a time delay on it. These models demonstrate that MCell can do dynamic geometry. I won't run it here, but MCell can do dynamic geometry. That's where the geometry changes shape in time. And these examples show how to do that. So this isn't yet fully supported in MCell 4, but it will be, pretty soon. But it's just a feature from MCell 3 that we haven't yet completely ported over to MCell version 4, but we will. And then there's these last 2 models demonstrate the how MCell 3 and soon MCell 4 can simulate the formation of spatial structure of the molecules. But right now, don't get too excited yet. Right now, the formation of the spatial structure is only in the visualization of the spatial structure, not in the actual interaction of the spatial structure within the simulation. That's going to come later. But we have 2 models that demonstrate that. Okay, so that's kind of the tour of the quick tour of the examples here. And now I think we're ready to launch into the hands-on part of the tutorial, starting with how to building from piece by piece the organelle model. Okay. So I'm going to start by, since I've been clicking on all these different examples, that probably has been kind of doing something to the state space inside here. So to make sure I'm starting nice and clean, I'm going to go up here to File, New, and I'm just going to say New General. And I'm going to say Don't Save what I've got here. So I'm not going to save any of that. And this takes us back to the beginning of a brand new, fresh model. Okay. And so the first thing we're going to do is, like earlier, we're going to select everything with the A key, and then I'm going to hit X on the keyboard and say delete. And this gives us a blank slate to start from. And then I'm going to type the N on the keyboard to open up the numerics panel and go to the Cell Blender tab and click on Initialize Cell Blender. And then again, stretch this to the side so we have some more space. Haina asks, could I show how to import and observe geometry from 3D raw or segmented image? Yes, we will do that during one of the advanced sessions, Thursday or Friday, if there's time to show how to do that. I think that's part of the plan. Actually, part of the plan on Wednesday, you're going to learn about Cell Organizer that can create 3D meshes from observed geometry. And then Jim says, I thought we were going to build a synapse, right? So I think I showed you that in my talk, and we did it in the talk, right? But building this organelle model shows you kind of the mechanics of how you put together, any model, and it could be a synapse, or has very reminiscent of a synapse. Okay, so here we are. We have a blank slate. So sometimes you want your studio to have a lump of clay, and sometimes you want a blank slate. So here we are in our blank slate. So so the workflow in creating a model from scratch is, well, generally we start with molecules. You could start with parameters and type in some parameters, but here I'm just going to start with some molecules. So I'm going to click on the molecules tab, and this gives us a list of the defined molecules, and there are none. So we're going to go to the right side of that and click on the little plus button here. This adds, and you can see that when I hover over the plus key, we get some bubble help that pops up, and it says add molecule, and then some help says add a new molecule type to an MCell model. So I'm gonna hit plus, and it comes up and it gives it a default name. Looks like Haina missed it. Did I open a new file? What I did was I went up here, I said file, new, general, to start with a blank slate, right? Maybe I'll go over that again. So I could do that right now. So let's, I'm gonna go say file, new, general. Don't save it. You have this. I'm gonna hit the A key on the keyboard to select everything, and then I'm gonna hit X to delete everything. It's gone. I'm gonna hit the N key on the keyboard. Go to the Cell Blender tab, initialize Cell Blender, and repetition's good. Soon you'll become experts at this. Now I'm going to click on the molecules tab. We get defined molecules, there aren't any. I'm going to hit the plus key to add a new molecule, and here's our new molecule, and it gets a name, molecule 1. Let's change the name of the molecule by clicking on the name field down here below the list, and I'll just type in the letter A for, let's just call it A, capital A. And there are two types of molecules we can have, volume molecules and surface molecules. Okay. Volume molecules diffuse in 3 dimensions within the space, and surface molecules are transmembranous proteins. I thought of as transmembranous proteins on the surface of a membrane-bounded compartment. Could be the cell membrane, could be an organelle membrane, could even be a scaffold, which is just a sheet. You don't have to have fully closed objects. Of course, an object that's not fully closed has no volume inside of it, and so wouldn't be compatible with BioNetGen necessarily, except that it could be just in BioNetGen and any of those physics engines that BioNetGen currently works with, not including MCell, those are all non-spatial. So a scaffold is no different from any other a scaffolded molecule is no different from any other kind of molecule, because they don't diffuse and they're just somewhere accessible to other molecules, right? So scaffolding doesn't even really factor in. Okay, so surface molecule and volume molecule, and we're going to give a diffusion constant. And if you have questions about what the units are here for diffusion constants, or questions about any of the fields here, there's a little info tab to the right of most of the fields, and you can click on the info tab and it will come up with some text about what to do. And sometimes there's ... in here because the text is too wide to fit. You can just spread this out and read the text. And it says the units are centimeters squared per second, which is one of the common units of diffusion constant, but maybe not the most common unit in biology. But at least you know what the unit is, and you can make conversions from other unit systems if you need to. So what we're going to do is here, we're going to type in a diffusion constant, 1e minus 6. So it means 1 times 10 to the minus 6 centimeters squared per second. And don't forget the minus sign there. If you forget the minus sign, then you'll be off by 12 orders of magnitude from what we want. Okay, so 1e minus 6 for our diffusion constant. And I can click on the info tab to close it again. And just so you can look here, below it gives us what the BNGL representation of that would be, and it just says A. That means A without parentheses. And I think in the way we implement things here in MCell, as of now in MCell version 4, the default reaction language is the BioNetGen reaction language. So everything is expressed here the same as you would in BioNetGen, except maybe putting in parentheses. See, if I put parentheses there, it doesn't like it, right? But I think in BioNetGen, if you have no components, expressing it with parentheses or without is equivalent. Maybe Jim can fill me in if that's correct or not. And if you want components, you can click on this little tab here and define components. So in here would be the list of components, and we're not going to make any, but you can see the plus. This is a kind of a common user interface motif. You have a list, and on the right side of the list are plus and minus buttons and some other interface buttons that you add or remove items from the list. But we're not, right now, we're not going to make any components, so let's leave that empty for now. And so what we've just done is we've added a new molecule type called A. That's a volume molecule that has a diffusion constant of 1e minus 6. So any simulation needs at least one kind of molecule. And then like in BioNetGen language, after you define the type of molecule, you need to seed those or place them, seed species, or just define species, is BNGL, is the BioNetGen language way of saying, put this many in the world. In Cell Blender and in MCell, we call this molecule placement. And so you click on the molecule placement tab, and we're going to say plus to add a new, what we call a release site. And they have a name, and we can just leave the name as release site 1. We don't care about that so much. We don't care to give it a different name unless you want to. and the molecule is going to be A. And now, because we're in 3D, when we place the molecules in the world, we can place them with a whole variety of different spatial distribution. And the default one is a spherical distribution at location in space 0, 0, 0 in X, Y, and Z. And then, but the sphere has a diameter of 0, meaning it's a point source of particles. Released with a probability of 1, meaning at the beginning of the simulation, these molecules will always be released regardless of what seed number we're using in the random number generator. So this means always release them at the beginning of the simulation. And then, so this is what, this is basically where and how, and this is how many, right? And so the how many is a quantity type. It can be a constant number or a Gaussian number, meaning with a mean and standard deviation. And it will vary by one trial of the simulation to the next. When you start up a new simulation with a different random number seed, it'll sample this Gaussian distribution, sampling how many to release, at the beginning of the simulation. You can also release by concentration or density. However, we don't have a volume here. We have the universe. We haven't made any geometry. And so it doesn't make sense to release by concentration because we can't fill the whole universe with. That would be, regardless of, as long as the concentration is bigger than 0, in an infinite universe, we'll have an infinite number of particles, right? So, so don't do that unless you have geometry to release in. So this is a spherical point in space at location 0, 0, 0 with diameter of 0, so it's a point source, constant number. Let's release just one particle. So any simulation has to have at least one molecule type and release at least one particle for anything interesting to happen. It's actually valid to release 0 here, in which case the simulation will run, but it's like running no simulation, right? Because there's no particles. So I'm going to put in one particle. And now I'm going to go to the Run Simulation tab. But again, like we saw with the examples, first I have to save the model in order for Cell Blender and MCell to know what to do with it. So at this point, I'm going to say File, Save, and I'm going to navigate to the directory where I want to save. So I'm going to go, we are already in the CMW 2021 first test directory. I'm going to go up one directory, and I'm going to add another directory here called organelle demo 1. Create new directory, yes. Okay, we're in this directory, and then down here, I can call this file organelle just demo. Okay, .blend, and then I say save. Okay, after I save it, now I'm ready to be able to run the model. And by default, we are going to run for 1,000 iterations in 1 microsecond. These defaults kind of come up automatically with the model. And so now I'm ready to hit export and run. And it takes us a second to export it, and then almost no time to run it. Boom, it runs really fast. And now I can say reload viz data. And it doesn't look like anything happened, but if I zoom in, you can see that right in the beginning, right in the middle, right at the very beginning, there's looks like there's 2 particles there, but don't worry about the one at the very, very center. Okay, there we go. if I hit rewind, it goes back to time 0. I'm not sure why this started at time 1 instead of time 0. We have a little glitch there. So here's our one particle in the middle. And if I zoom out a little bit and I hit play, I can see our particle diffusing. And this at the center is just a marker that contains the shape of this of the glyph used to draw the diffusing particle. So I'll explain that more about that in a minute. So just ignore and don't worry about that in the middle. This simulation really does contain only one particle. And so this is what random walk diffusion looks like with one particle. And it looks like the particle's way over here on the side. And if I look from the side, we can see the particles moving below the plane of the Cartesian coordinate system. And if I use the keys, the view keys on the numeric keypad, key 7 looks from the top. So here we are looking from the top, and here's our particle diffusing over there. Let me get rid of this thing over here. Here's our particle diffusing from a top view. Here it is from the front view, and here it is from the viewing from the right and top. And now it automatically loops back and starts again from the beginning as it goes. So here's our one particle of molecule of A diffusing and undergoing random walk. And why isn't it spending more time on average close to close to the origin? Here it looks like it went to one side and it's kind of staying to one side. Well, this is what random walk looks like. It randomly walks in space, and it can randomly end up way over here. Looks at the beginning, it spends some time kind of moving around, but then it starts moving off in this direction, and then now it's moving over there. This is what random walk looks like if you look at only one particle at a time. And it looks like there's a bias to it, but that's how stochastic things can behave. If you only look at one, you're being biased by the one that you're looking at, right? It's really our view that's being biased, not the behavior. Okay. So now I'm going to rewind this back to the beginning and maybe look from the side again. Let's see, let me zoom out a little bit. There we are. Open up a control panel. Okay, so if there aren't any pressing questions, I'll keep moving forward with this. Oh, yeah, I see someone's asking about units, and Randy had earlier asked about units. So there is a way to set the units, but unfortunately, it's kind of broken in Blender. Not my fault. We need to talk to the Blender authors. In units, they have things set up very nicely. I was very encouraged by this, that it's in the metric system and length meters. And one of the units here is micrometers. Don't do it though. Don't do it though. It's broken. Everything works up down to millimeters. But when you get to micrometers, it's broken. So they have some precision problem where anything finer than 10 to the minus 4 in some internal conversion factor, anything smaller than 10 to the minus 4 is broken, and micrometers is 10 to the minus 6. So we need to talk to the Blender developers and get them to fix what they're doing inside Blender when you convert to micrometers. It's pretty awful. So actually the best thing to do is, if you want to do it right now so you don't get confused, because it says meters, right? But it's really not meters. Best thing to do is go into the unit system And you get to that by this, let's see, 1, 2, 3, 4, 5, the fifth tab on this lower right-hand side. It's called if I hover over it, this is called the scene properties. If you hover over it, you can see it says scene properties. Units, open up units, and under unit system, click on it and then select none. So it's safer to set none so that you don't get confused. And in MCell and in Cell Blender, the default unit for length is micrometers, and the default unit for time is seconds. And we'll get onto the other units. Jim touched on it yesterday. For reactions, we'll get to that when we start making reactions in our model here. Okay, so in the run simulation tab, you can see your completed runs here. If you want to clear out the list of completed runs, you can just say clear runs. All that does is clear its name from the list. Doesn't clear the result that we got. Here's our particle still there and still diffusing. I'll rewind this back to 0. So next thing we're going to do in our tutorial is we're going to go to the molecule placement, and we're going to increase the quantity to release from 1 to 1200. So let's release 1200 molecules of A. And then all we need to do now is go to run simulation and say export and run. And there it goes. And who thinks, when I hit play, who thinks we're going to see all the molecules wandering off in one direction with a bias? Hopefully nobody. So I'm going to hit play. And what we see is a radially symmetric, Gaussian blob of particles. If I zoom out like this, you can see this Gaussian blob. So curious thing about diffusion is it looks like it goes fast at first, and then it looks like it slows down to like molasses. And that's the nature of random walk. Each particle has an equal probability of moving in all directions. So why does it look like they move outward, away from the center? Well, that's just a matter of probability. It looks like there's a force that is pushing them apart. But I promise you there is no force making the particles move down their concentration gradient.
Right.
And when you look at the diffusion equation, it looks like there is a force that's pushing things down their concentration gradient according to the magnitude of the gradient. There is no such force. It's just it's a misinterpretation of the equation to think that it means that there's a force pushing them apart. There is no force pushing them apart. The reason why it looks like they're moving away from each other is because initially, or at any point in time, if you're near the boundary, there are no particles outside and all the particles are inside. And so the probability that a particle moving outward is going to be replaced by one moving inward is 0 if you're beyond the edge of this, right? So the particles will diffuse and move at random wherever they're going to go, and but if they happen to move outward, there's no particle that can move inward and replace them. So if they move outward, they've expanded the domain of the space that the whole population is occupied. Okay. So there's our
so
yeah, go ahead.
would you mind showing your release pattern settings one more time? Because I'm getting an error message when I run simulation.
Okay, So, so it's not release pattern. So you shouldn't have anything under release pattern. So a release pattern is a temporal pattern. Someone had a question about, can you release things at different points in time? And the answer is yes, you can use the release pattern to be able to do that. But we're not going to go into that right this instant. There's some tutorials on MCell.org that show how to use that. But molecule placement is where you want to be.
Right, but it looks like you have a set settings. Is that automatic settings to 0? And you actually have the molecule A there, but
yeah, you have to type in the letter A. And it's
Where-
case sensitive. And
in-
it's case sensitive. So you type in capital A for the molecule.
oh, you're on the molecule placement. Okay, I'm sorry. Yeah,
Yeah, you have molecule placement.
right.
Yeah.
Well, so you need to type the actual name of the molecule there that we created it.
Yes.
Okay. And that's the one
Oh.
we see earlier in the directory. I see.
Under molecules, we have defined the molecule called A. And then in molecule placement, we place the molecule called A, but we actually have to type that in.
Oh, okay. I think that's the step I was missing because it gives me an error message saying that it can't run
Yeah,
due to the fact that I can't find the thing. Oh, okay. Thanks, Tom.
yeah,
Appreciate it.
yeah. Now we can always do better with the error messages and error detection in the way we do things here. So your question is not a silly question. Okay. So hopefully that will work for you. Okay, so now our next step in our setup is to go to molecules, and we're going to add a second molecule type, and we're going to you guessed it, we're going to call it B. So add a new molecule type, give it the name B. It's going to be a volume molecule, and let's give it a diffusion constant of 2e minus 6. So it's going to have a diffusion constant twice as high as A. And then in our molecule placement, we're going to add a new release site. And we're going to release molecule B. And it's going to be spherical. But instead of releasing at 0, 0, 0, we're going to release at an X location of 0.2. And that's going to be, I'm going to say 0.2. That's going to be in microns. These are in units of microns. And we're going to release 1,000 of B as a constant number. So constant number means on every instance of the simulation that we run, we will always get exactly 1,000 of these molecules, and it won't be sampled from a Gaussian distribution or any distribution. It's always going to be exactly 1,000. Okay, and we're going to release those at X location 0.2, Y0, Z0. Okay, and just for good measure, I'm going to save my simulation under the, just say save, not save as. And you'll know that it's saved by looking at the bottom near center of your window, and for a moment it'll say saved, right? And there's a hotkey for saving, it's Control S, and you can see it says saved organelle demo.blend. And that stays up for a moment and then goes away. Okay. And before I run it, I'm going to rewind time back to 0 just so we can see how things start after we reload. And okay, under run simulation, hit I'm going to clear the completed runs and hit run again. And it takes a moment to save. And then there it goes. And then if I hit reload, we can see a little dot at 0.2 microns away from the center where the B molecules are going to be released from. And here I can hit play, and there they go. And you can see, and then I'll hit stop pretty quickly, and you can see that the B molecules are colored green, and they're centered, they're centered at 0.2 microns, and they've moved farther in less time than the molecules of A because they have a higher diffusion constant. And if I hit play, then there they go. And if I go back to the beginning again, another way you can advance time is with the left and right mouse, the left and right arrow keys on your keyboard. You can single step forward and backward in time. So it's kind of fun to go backward in time. So if I go forward a lot and then hit play backward, then you can see everything going back. So it's kind of goes in a direction that time doesn't normally go. It's kind of fun to watch. Okay. So at this point, I'm going to hit Control S again to save. And at this point now it's 12 o'clock and time for our lunch break. So I think we should do that. I promised to stick to the schedule today. So I know some people have a meeting that they want, meetings that they want to go to during lunch and then come back to us after lunch. So, and when we come back after lunch, we'll be on a different Zoom channel. And so, yeah, so let's leave it there. Unless, people want to leave to go to their meetings, do so. If anyone has questions, I'll stick here for a moment to answer any pressing questions. Yeah, so Randy says the release sites are 200 nanometers apart. Yes, because 0.2 is microns, which is 200 nanometers. Yeah. And someone says, doesn't look as asymmetrical. Not sure why. Show the release placement parameters again. Okay, so under molecule placement, we have release site 1, which is 000 XYZ, diameter 0 and 1200 to be released. And release site 2 releases molecule B at 0.200, diameter 0 and constant number 1000. Okay. And that should do it. And to get the same result that I'm showing, you need to have the same input, right? Okay. So someone asked for a cheat sheet for Blender keyboard shortcuts. I think there is such a keyboard shortcut available on the internet. Maybe during lunch, I'll look for it and I'll post it somewhere. Be careful about getting old cheat sheets because the new version of Blender is slightly different and will need an updated cheat sheet. So I'll see if I can find the latest cheat sheet for it. Okay. Okay. If someone sees that error, Akash Banerjee says he's getting an error that says expression cannot contain assignment. Perhaps you meant equal. I saw that last night when I was going through this. That happens if you don't put in a quantity for the number to release. So that's kind of a weird error message, and we should fix the error message to be more clear. But I think what it means is that it happened to me when I forgot to type in a number to release. So Akash, maybe double check that release site 1 and 2 both have a non-blank quantity to release. So if I zero this out and it's blank, watch, I'll demonstrate. I'll hit run simulation and it'll try to run. Hello? Uh-oh. Not sure what just happened. There it goes. I think I forgot to hit run, export and run. Okay, So if I run that, then I get perhaps you meant equal, right? And that happened because I accidentally left the quantity to release field blank. So I'll put in 1,000 there and go to run, clear my runs and hit export and run. And now it's happy. And there it goes, it's running. And I got my result. Okay. See a field for charge molecules. So we don't yet have charged molecules here in the user interface, but MCell 4 has capabilities now. It's brand new, right? And MCell 4 now has capabilities that we haven't even scratched the surface of yet ourselves. And it would be possible to replace in MCell 4 in the Python interface for MCell 4 that Adam will show us on Thursday. It's possible to write your own functions. We haven't tried doing it yet, but it's possible to write your own functions to make things behave in different ways. For like with charged particles, perhaps, and advection. That means diffusion with drift. It's possible to do these things now, or at least in principle should be possible to do things now.
Right, in principle, but this specific feature needs some extensions. But
yeah, but we're poised to be able to do these kinds of things. And Lenka asks, can you use geometry nodes? So the geometry nodes, I think, are special geometry functions that are built into Blender. I think in principle, you can do everything with geometry. Anything that you do with geometry in Blender should be able to generate geometry that is compatible with MCell. And so I think the answer is yes. And to make things happen dynamically, we would have to tweak the dynamic geometry functions that are demonstrated here for MCell 3. We would have to tweak those to work with MCell 4, but I think it wouldn't be too hard to do. And these are things that we'll be helping do, and you know, this is all open source code, and anyone in the community, including you guys, are welcome to team up and help make some of these extensions happen. Okay, so I'm going to run, and if there aren't any more questions, I'm going to sign off and get my lunch because it's lunchtime.
So, okay, so I will close this session then, if it is okay with everyone. So come back and use the new Zoom link. I will share it in the, and before everyone leaves, please fill a day one survey, because we really want to know what you think about this workshop. So it helps us a lot. And I will share another one either at the end of today or tomorrow early in the morning. Thank you very much.
Okay, see you all at 1 o'clock Pacific time.
And
okay.
1 o'clock. Okay.
Okay. Bye.
Bye-bye.